In this video lesson, we are going to discuss electric potential due to a point charge. Let us consider a point charge Q produces an electric field and that is radially outwards because this particular charge is a positive charge. Now we have to find out the electric potential at this point P, and the electric potential is denoted by the letter Vp. By definition, electric potential is the work done to take a unit charge from infinity to this point. Electric potential at any point in an electric field is defined as the work done to take a unit charge from infinity to this point. Consider this point is at a distance r from the source charge, and I am taking a charge q0 from infinity to this point, and imagine p dash is an intermediate point at a distance r dash from the source charge. Now when the charge q0 comes here at p dash, it experiences a force F is equal to q0 times E. F is equal to q0 times E is the electrostatic force experienced by charge q0 when it is kept at p dash. Now in order to move it further forward towards source charge q, I have to do external force. At least equal and opposite force needed. Therefore, force given externally to move the charge q0 opposite to electric field F is equal to minus q0 times E. By giving that much force, let us assume that the charge is displaced further through a small distance dr. Then the work done dW is equal to force times force into dr, or F dot dr. Since theta is equal to 0 means force and displacement are in the same direction, I can take F into dr, that means minus q0 E into dr. What is this dW? It is the small amount of work done in order to move a charge q0 against the electric field through a small displacement dr. But the definition of the potential is the total work done to move the charge q0 from infinity to this point at a distance r. So the total work done W infinity to P can be obtained by the integration of the small amount of work done from infinity to the radial distance r. R is the position of P from the charge. So W infinity to P is equal to integral infinity to r dW. Substituting the value integral infinity to r minus q0 E into dr. Now minus q0 can be taken out and q0 can be taken to the left hand side also. W infinity to P by q0 is equal to minus integral infinity to r E dr. Put as equation number 1. Yesterday we studied potential at the point Vp is defined as work per unit charge. W infinity to P divided by q0 is also the work done, Vp. Put as equation number 2. Now I can compare 1 and 2. When I compare 1 and 2, I can write Vp is equal to minus integral infinity to r E dr. This equation yesterday also we derived. Now, what is the next step? What is E at the position P dash? P dash is at a distance r dash from the source charge. R dash is a movable. R dash changes from infinity to r. So, a lower limit is infinity, upper limit is r. Where is the final position? So, r dash is the position of the charge right now. Therefore, electric field at that position can be written as, due to source charge Q, can be written as E is equal to 1 by 4 pi epsilon 0 Q divided by R dash square. Why it is R dash square? Because our test charge experiences a force due to this electric field at P dash. That is why electric field is 1 by 4 pi epsilon 0 Q divided by R dash square. Now if I am substituting in this equation, I will be getting Vp is equal to minus integral infinity to r. Instead of E, I will be substituting this. 1 by 4 pi epsilon 0 q divided by r dash square into dr. Now q by 4 pi epsilon 0 can be taken out along with the minus sign. Q by 4 pi epsilon 0 is taken out. Integral infinity to r 1 by r dash square into dr. So that will be the potential. Now that can be written as minus q by 4 pi epsilon 0 integral 1 by r dash square can be written as minus 1 by r lower limit infinity upper limit r. What's the meaning of that? R dash can take the value from infinity to r, where r is the final position. So we have to take the charge from infinity to r in order to find the potential Vp. Now substituting the upper limit and lower limit, I can easily find out the potential at any point Vp is equal to 1 by 4 pi epsilon 0 q divided by r. Look at the potential. There is no need of r cap or x cap, whatever it may be, because potential is a scalar quantity, no need of vector notation. That is number one. Number two, the potential electric field equation we already studied, 1 by 4 pi epsilon 0 q divided by r square, but the potential is V is equal to 1 by 4 pi epsilon 0 q divided by r only. So the inverse dependence of potential with distance is 1 by r, proportional to 1 by r only. Now if the charge is placed in a medium of relative permittivity epsilon r, then potential at any point r can be written as Vp is equal to 1 by 4 pi epsilon 0 epsilon r q divided by r. Now what are the dependence of potential? Number one, V inversely proportional to r. So that means r increases, V decreases. Away from the source charge, potential decreases. As we go radially outwards, the electric potential decreases. Number two, V proportional to 1 by epsilon r. As epsilon r increases, V decreases. What is the meaning of that? As the relative permittivity increases, electric potential due to a charge or a charge distribution decreases. Now, as I said, electric field can be written as E is equal to 1 by 4 pi epsilon 0 q by r square. Now what is the dependence of distance and electric field? Electric field is inversely proportional to r square. Electric field is inversely proportional to r square, but electric potential is directly inversely proportional to r only. Now if I am drawing a graph connecting electric field or potential along y-axis and the distance along x-axis, the electric field variation with the distance is little bit steeper than electric potential variation with the distance. This is because electric field is inversely proportional to r square, while electric potential is directly inversely proportional to r only.